So this part is where we actually learn about the neutrino oscillations, and it's actually be detailed. And this is very unique of this neutrino oscillations in supernovae. So from say like last, I can tell you like for last 20 years, every year the results were something new, in a sense like whatever we were doing the last year came out to be probably not true. So it's like a constant updating. The reason is of that is like because it's a non-linear problem, and there are a lot of assumptions people did in the very first. We are doing for the first trial, you will make assumptions and try to do the simplest problem. People try to do that, and as you keep removing the assumptions, the picture were just simply going. I mean, the picture from last year was completely changing, and it kept doing that. So what I'm going to do is I will go in a chronological way. Chronology samajhte ho na. So we will do like a chronological way. So it's more like a historical perspective how this thing came up, more or less like that. You can just look at it like a storytelling way, because we are not going to do much any calculation here. But and whenever you feel that you did not understand anything, you can stop me. Okay, so this is what we were doing in the morning. Here we have our supernovae neutrinos in energy. In MeV energies, we learned a bit about how they are produced, and then about possible detectors. But this part we did not discuss much, other than realizing that the flavor conversion behind the shock might actually be useful if you can oscillate among these flavors. And this is how we know about the neutrinos. And as you can see in the schematic one, like the inputs to the explosion model in the outputs of the neutrinos is where we are interested in. But this flow chart is without any neutrino oscillation. So when they were taking this neutrino physics in here, so the simulation, the people who are doing hydrodynamic simulations, they are not considering any information about the neutrino oscillation. So if you want to do that, you have to do it like post facto. After they give you the fluxes, on that you have to do the oscillation. This is what we also saw in the morning, that we had there are three distinct phases: the neutronization burst phase, mostly in electron neutrino, the accretion phase, and of course the cooling phase. And in these two phases, we had a very large flavor asymmetry. So if you want to study oscillation, this is where you are interested in. Also from the perspective of supernova mechanism, you would remember like this is like around this time is where the shock is actually failing and it is stalled. And if there is any input to the shock energy, it would come from neutrinos, it would be here, and this is where you want to look into the oscillation effects. This is in the accretion phase. And of course, here you have a large flavor asymmetry, probably oscillation effects might be important here. This is also something we learned in the morning, that we had this neutrinosphere. This is the last scattering surface of the neutrinos, which is very similar to what Yvonne told you, like in the early universe, you have this neutrinos freezing out, this same thing. So neutrinos were in like with all these interactions, and as the shock broke out, the neutrinos are now allowed to move, because as the shock breaks out, the density falls down, and the neutrinos now can actually diffuse out. So this is what you call the neutrinosphere. Analogically, you can also call it the last scattering surface of your neutrinos. Now neutrinos are coming out. While coming out, they interact with other neutrinos somewhere here. This is what we call the neutron-neutron interaction. Further out, you have the normal MSW scenario. And then this is also something I pointed out, that very close to the neutrinosphere, you have something called a fast collective oscillation. And as you go further out, around 100 kilometers, you can have something what is known as the slow collective oscillations. We are going to look into these different oscillation effects in some detail. Now, probably the first equation from morning. So this is your neutrino transport equation, or the evolution equation. So here you are going to deal in terms of the matrix of densities, where the diagonal elements tells you about the the flavor content, and off diagonal elements will tell you if there is any oscillation among these flavors. This is like a Liouville-like equation. This is something probably we often do like when studying neutrino oscillations, that it can be studied, can be like analogy to like a spin system under magnetic field. If you remember there, this the vacuum ones, they actually act like this, give this analogical magnetic field, right? So now this is a similar scenario. You can also do this thing now. You can take this block notation, can write them in terms of the polarization vectors. If it's a 2 flavor, you have 3 polarization vectors. If it's a 3 flavor system, you will have 8 of them. So this is something probably some of you might have done, but this is the same structure. What you have here, this is your mass mixing term. This is the matter term, which is the dynamical MSW term. And in this case, we have already seen like when the neutrinos go out, they can interact with this electrons, and this gives you this MSW term. And this is this new term that we are looking at. This is the density of neutrinos, or which comes in here. So this is called the neutron-neutron interaction term. You can see this depends on the rho itself. So now, if you plug that back in, what you are going to have is, firstly, you are going to have like in this term, in the interaction term, there is rho sitting, and when you do this commutation, you are going to get a nonlinear equation. Now let's see what are these different suffix or these indices here. See what I'm saying, that this is actually a 7-dimensional problem. So in which way is it a 7-dimensional problem? In principle, this is not a problem where you have, say like long baseline experiment, you have like the neutrino beam only going, right? And at every time, so you are not looking at this problem from say like a long baseline perspective. It's not a problem which is evolving in time. So at every time, you have the same, you can think like whatever you are doing at every time is something similar happening, right? But in this case, we already saw there are different neutrino emission phases. So this problem is evolving in time. So taking a stationary solution to begin with is not probably the best thing that you can do. So you will have a delta term. And of course, as the neutrinos evolve, they come out of the star, they evolve. That gives you the evolution in spatial. So here it's firstly like you have both time and spatial evolution. Now, we will see like, so basically you can understand 1 plus 3 of them, but what is the other 3? The other 3, let me see if I have the diagram, it comes much later, but let's come here. Okay, this is probably here we can understand. So probably if you are not aware of this field, so usually you will think of like neutrinos coming out of the star, it's like coming out from the center, and center in your mind is like a point. But as you saw, it's not a center, it's not a point, it's a sphere. Now when neutrinos are coming out of that, the thing that we are discussing, that neutrinos which are coming out of the neutrino sphere, they are interacting with others. So for example, the neutrino which has come out of here in this direction can interact with someone coming from that direction, right? So this, when they are crossing, at every point on the neutrino sphere, neutrinos are just diffusing out, right? You can think of one point on a sphere and all of them are diffusing out in different directions, right? And the same thing happening, say like a nearest point. So now when they are interacting, you have to take care of the angle between them, and you have to also keep track of like what is this V dash. V dash is basically, you can think it like a evolution equation for a test neutrino with velocity v. V of course tells you the direction of the neutrino, and all other neutrinos, because you are integrating over them, all other neutrinos which can interact with your test neutrino. Just imagine you have one neutrino coming out of from here, and all other neutrinos from different points which can interact with that neutrino. So these are my V dash. So then when you are writing the matrix of densities, this many let's say indices will come for that. At what time, at what radius you want to see this, and of course we write like say like energy we are saying, and at what angle it actually came out. So it's actually what you have is a 7-dimensional nonlinear problem and nonlinear PDE, but that's not all. As you can see, this rho which depends on this, they are actually interacting with all other V dashes, right, the V. Similarly, if you want to write the equation, now you do not know the solution of this V dash. So you can write a similar equation for the V dash, but the V dash will have a term which depends on all other V's. So it's like a nonlinear PDE in 7 dimension. On top of that, you have it's a coupled one. So it's a coupled nonlinear PDE system. It's very difficult to solve numerically. So now this is what people had in the beginning. V dash is like unit vector. Let's say V dash is the direction of the velocity of the neutrino. Say let's say I have we will have a schematic diagram later, but let's say this is my V. The neutrino is coming out radially, and let's say from here another neutrino which came and interacted with this one. So now the angle of that neutrino I am putting in that variable V dash. So similarly, you can have like many neutrinos from different parts of this sphere would have come and interacted with your test neutrino, and so you have like many possible V dashes, and you integrate over all those interactions. So this is what people had to solve if you really want to understand the oscillation of neutrinos, if you have this neutron-neutrino interaction term. Now, but this came out to be in prominence in say like I mean the first time people realized these things were like in the early 1990s. So in the beginning of 2000, people started looking into it more carefully because before it was not possible to solve this. I mean, it was not easy to solve such a system. And of course, the analytical understanding of this also increased. Now you probably understand why people started with a very simple system and why every second year or every year we have a very different phenomenological possibility while treating them, because as we numerically progressed, you take out one assumption and the results changed. But then let's say I do not have this, let's assume a very happy scenario that you do not have this neutron-neutron interactions happening. So then I only have to take care of the MSW. And as you can understand and probably have heard, like in supernova, even the MSW is not as like for example in long baseline or in solar cases, because you have all three flavors. The level crossing diagrams were definitely more complex, and it could happen for both neutrinos and antineutrinos. Here, like this is from this famous Dighe paper, and this thing was like even more complex, because now we live in a much easier world where you know the values of θ13, you have some idea of the mass square values. So because those are going to decide about your jump probabilities, right? The pH and PL. So you have like, as you can see, like you can have one at, so this is the increase of the density of electrons. So your core for this problem, the center of the star is somewhere here. As you are going out at a higher density, you have like one resonance, and at lower density you have another resonance. People call it pH and PL. If you go and this paper is very prominently used. But when they were doing it, they didn't know what are the values of these angles, and it was so difficult to calculate what was the pH PL. So if you go back to this paper, even that was like the one of the reasons this paper is also famous, because it simplified what people were doing even earlier. So for different scenarios, there is a different of result which came up, but of course this is like almost more than 20 years now. So now with the value of the mixing matrices, that or the mixing angles that we know, you can calculate the pH and PL, and if you do not have any collective effect, your flux expressions are pretty straightforward. So what you have is like, if it's a normal ordering, the nu e is basically depends on the nu x. X0 is basically, nu x is nu mu bar, nu tau bar, nu bar tau, and 0 is the initial flux, the flux inside the star, and this is the flux what you would expect at the detector. It depends on the initial flux in this way. For example, for the f nu bar, of course, it depends on the cos square θ12 and sin square θ12. So this is the flux expression one can use if there is no collective oscillation. It's reasonably straightforward. If you have to just go, and if you have not looked into this paper, please have a look if you are working in for example, in long baseline, or like where you have to really deal with neutrino oscillations. This is actually a very different example than the kind of systems that you usually deal with, which is definitely more complex, but this is also something very interesting. Okay, so this is the flux scenario that you would get, but then so this is basically happening in the early 2000. This expression is, we know, let's say in 2010 onwards, where you already have some idea of the θ13. But before then also people were looking into different scenarios and what could have been the effect of this MSW oscillation without any neutron-neutron interaction. So this part of the discussion, let's assume there is no collective effect or neutron-neutron interaction. So this is known as this shock wave effect. So what is plotted here is the radius and the density of the electron. Basically, the matter density, how is it changing for some 1D simulation, and how is it changing for different time. So this is like this is the 0.1 second matter density profile. As you move along time, as you can see, this is the shock front. The shock front starts moving outside. This is, we saw in a different way in the morning figure. So here, as you can see, that the shock front is moving ahead. And the resonance density for these neutrinos for both rho h and rho l, if you know, so root 2 GFNE, you can actually plot it here. So this is the resonance zone, and once this shock will, or the neutrinos will move through this one, we are going to have some shock wave effect. What is the meaning? For example, if you look at this black curve at 0.1 second, you can consider it to be something like a very adiabatic problem. But at the shock front, when the shock front goes through this area, you can have a non-adiabatic scenario, and there can be this matter effect, matter and resonance oscillation. So this is what people try to look for as in the what we call the shock effect, and this is how the events per bean people thought at, I mean for the shock effect would look like. As you can see, this of course for the scenario where then at that time people were doing for different cases, like different values of θ13, like large θ13, small θ13, large θ1, because you didn't know even probably at this time around people had some idea about the PL, but the pH was still not known. So people were doing different scenarios. I have just given the example for when θ13 is not too small. So as you can see here, so this is the event, suddenly there is a drop. This is for and between and this oscillation scenario, as we have already seen, no, this will also change because in the ordering. So there are like two different scenarios. So inverted hierarchy with shock and inverted hierarchy without shock, and this is a normal ordering. So this was the shock effect was also thought to be a way of distinguishing mass ordering. And the same thing, this is for a hyper K kind, this is for ice cube, how one can see the numbers actually changing over time. So this is where in the morning we were saying, so there are, when do phenomenology, you have to think whether what is important for you, whether the time spectra or the energy spectra. Here what you are looking at basically what we call the quote unquote neutrino light curve. So how the events are changing over time. But of course in supernova things are always not so easy. Then people realize that this is a very, so see, everything depends on what the people doing hydrodynamic simulation is providing. So if you look into here, there is not a much problem because there is only one non-adiabatic case, there is only one oscillation. But life is not that simple. What you actually have a scenario like that. This is the shock front. People even thought of like a forward shock, backward shock, but there can be turbulence. So you remember today we were saying in the morning, this is like a working simulation, 2D results, we are saying about convection behind the stalled shock. Here you can see how the densities are actually changing, these convective currents. And so that would mean that behind the shock, you do not get a very smooth profile. You have a profile which can have many non-adiabatic scenarios. And if the neutrino oscillation goes through that, you can have several of these jumps or like change in the probability, and you can actually lead to depolarization. And so regarding this, there are like many discussions. If you go back to literature, you will find like many scenarios, many different possibilities. People try to look for sterile neutrino solutions from here, like sterile neutrino oscillations, and how they are going to change these effects. However, what is the actual scenario? So this is something we did. So this is for with the turbulence. So this is, as you can see, this is the jump probability pH. So you would expect for some energy, if you go back here, so for some energy it will start. If you had a smooth profile, you would have had the pH going up, then the pH coming down as you go further in the energy, right? But if you have this kind of turbulence, you are going to have this this very different kind of a probability scenario. And if this turbulence was very large, if you had like enough fluctuation in this small length scale, people would have expected like a damping in this pH. So this is something what we did like some time back. We looked into the 2D simulations from Garking, because to do that, what do you need? So eventually we are looking at the simulations data, and when you look at the simulation data, you want here like precision, right? So at which precision in spatial precision they are actually keeping the data, right? So for example, in 2D simulations, people have started looking keeping the data at a reasonable precision, but eventually you want to do it for a real 3D simulations. There the data is not yet this precise. So whatever we had, we looked into that, but what we found that there is not enough fluctuation in the small length scale because of the precision of this simulation data. And if I don't remember exactly, but maybe this was like of the order of few tens of kilometers or few hundred kilometers, like at which they are actually keeping the data. You need even precise one for 3D simulation. So we are still further out from there, but whatever you have, because that's how we can talk in science, right? So with the information at our hand, we found there is not enough fluctuation in the small length scale. So the turbulence effects are there, but like exactly how important are they? We have to still wait. And now, so this is like one example of what people could have done if this neutron-neutrino interaction was not there, if collective oscillations were not there. So this is one way of understanding this collective oscillation. So what is happening is your matter density is falling as 1 by r cube. However, this mu, which will come very often, which is basically root 2 GF n nu, that is the neutrino density, and this neutrino density actually falls as 1 by r to the power 4. But the important part is, like in the beginning, at that very small radius, this neutrino density is extremely high. So what happens that in the beginning, if you go back to our traditional picture, is like, so in the beginning, the neutrino density is extremely high, where the neutron-neutrino interaction effect is important, but it's falling as 1 by r to the power 4. So within a reasonable distance, like between 10, 100, few hundred kilometers, this collective oscillation actually starts becoming non-important. This is the scenario, and this V this is also sometimes called the lambda. So in the next many slides, we might actually have this mu and lambda. Lambda is basically effectively the matter potential, the electron density. Mu is basically the neutrino interaction strength, or basically the number of neutrinos. This is one way of understanding this difference between this collective oscillations, also called the self-induced flavor conversion, and your normal vacuum and the MSW flavor conversion. See, like if you now look into the detail, that the vacuum and MSW oscillation, the oscillation depends on the energy, right, of that neutrino. So for a specific given momentum and for a given mass square difference, you can figure out the oscillation, and the oscillation depends on something like this delta m square by twice e. So this is what we often call as omega, delta m square by twice e, and for a typical supernova scenario, for a typical star energy of like 12.5 MeV, this comes out of the order of this kilometer inverse. However, the moment you start looking into this neutron-neutron forward scattering, what do you require here? You require a very dense medium, because we understood it's like a collapsing stellar core or early universe where you can have such a scenario. But this can happen without masses and mixing. So this is like a neutrino oscillation, but that does not require neutrinos to be massive. I mean, okay, this might, you might get a wrong information, wrong idea, but here, the point is like, in principle, you can have this oscillation without the neutrino masses. Of course, neutrinos are massive, that we know, so masses have some effect on this kind of oscillation, but in principle, this does not require the delta m square by twice e. All it requires is this mu, what we are calling as root 2 GF n nu, and as we have realized, this is actually much smaller in the inverse length scale, and this can happen for these typical numbers. This is of the order of this 0.5 centimeter inverse, and as we realize that this can actually happen very close to the neutrinosphere, behind that stall shock can be important for shock reheating. And this was our system in 1 plus 3 plus 3, the 7-day system. What did people do in beginning? So this is the chronology that we are coming to. So of course, being a physicist, the first thing you are going to say, I don't care, I am going to look at a stationary problem. So get rid of this one for time. And then I really don't, I think all the stars are actually spherically symmetric. I am only going to look at the radial evolution. I am not bothered about what is happening in the other direction. So this, I am going to only look at a radial one. This is not a vector, this is only del r. And what is the other three? Other three were like the properties, or say, let's say here you have this t, r as a vector. In principle, r could have the r theta and phi for r, and this e is the energy of the neutrino. The v tells you at what direction the neutrino came out. It can be like, so there are two directions here, two different set of angles. So realize one is during the evolution of that neutrino coming out of the star, at what do you want to only look at the radial evolution, or at every point you also want to see if there is any evolution happening in the orthogonal plane? We will come back to that. So that is this r, and this v tells you from the surface of the last scattering surface at what angle the neutrinos actually came out. So here I have another set of angles. So what people did to begin with, they said like, okay, let's assume all neutrinos are coming out with the same angle. I only want to look at the radial evolution, and there is no stationarity problem. And my problem is a stationary solution. What can I do with that? What can I understand? So this is what people were trying to do. Here is like a schematic thing, what is happening. So this is your neutrinosphere. And you can imagine this is a 1 plus 1d1 scenario where at every point on this surface, you are actually having neutrinos coming out in all possible angles. And these neutrinos should interact and give you the result. Now you go to this 0 plus 3 plus 3, it's a stationary emission, same idea, but you are just thinking, so you are basically taking a snapshot of the star at some point and saying, okay, this is the scenario for the whole duration. This is the stationary case. Then this is the scenario where you say, okay, I have an axial symmetry around the z-axis. I only have a z-axis. So here you have only r and theta. The star is exactly same at all points in here, right? So at different of this color, you have a similar picture. Then if you go to even a much more simpler scenario, that you have a spherical symmetry about the center, that is, I am only going to look at the radial evolution of the problem, but the emission of the neutrinos can happen in all directions. So this is what you call the multi-angle scenario. Then you say, okay, let me do a simpler scenario where I have only the angle, this theta angle, what is important, not the phi. So this is this E theta. And so this is what people used to call the multi-angle and the bulb model. But what people actually started with this scenario. So this is the simplest thing that can happen. Neutrinos coming out radially from here, and all of them are coming out with the same angle, and you are just want to see the evolution in radial. But then coursework or even in masters, BSc, you do a very simple model, just oversimplified model, but you start getting some physically important results. You get some understanding of the system. This is exactly what people did in the beginning. the single angle model. This is what you are solving eventually. And when they did, this is like, say, the first thing that they found out, synchronized oscillation. What did they found for this system? Here is the spectra at different energies. If you remember that for the vacuum and for the MSW, the oscillation depends on the energy. For example, if it's a vacuum scenario, if you do not put this neutron-neutron interaction term, different neutrinos with different energy, they have a very different oscillation frequency. But the moment you switch on this neutron-neutron interaction 1, a large neutrino density, all of them start showing you the same synchronized behavior. All of them, this is again like exactly like a polarization vector scenario. The moment you actually switch on this thing, all these polarization vectors, they basically club, and the motion is actually of the mean polarization vector. That motion is actually followed by all the particles are following the mean motion. So these are also put in the ways of mean field theory. We were going to there are like lot of discussion. There are papers where people actually try to look into this system in comparison to condensed matter systems. You can probably understand already if you think back of the different systems you have studied in your MSc days, like for different condensed matter system. This is in a very similar. So people have, there is this very nice discussion where people show this very simplified system can be thought of like a superconductor, where these different neutrinos are like Cooper pairs, and so evolution of one is connected to another. So this is what we used to call the synchronized oscillation. Then they found something called a pendular oscillation. What was happening? Now, equal densities of nu and nu bar in the inverted hierarchy. People were initially looking into the inverted hierarchy, and as they switched on this thing, they saw that this is a probability. This is written pz bar, but let's say this is the probability. These are actually this z component of the polarization vector, which is important for the probability. But let's say this quantity, as you can see, changes between 1 and -1. If I call it probability, I cannot write -1 to 1, but this eventually leads you to probability. So the probability goes between 1 and 0 for this scenario. So there is like a pendular oscillation happening. And there is then, at that time, there was a long discussion that this system can be written like a pendulum, like an inverted pendulum for the normal and the inverted ordering. And just like a coupled pendulum system, they were like analogy for this very simplified system. People actually did all this analysis, and that helped the understanding of what was happening. So in inverted hierarchy, coherent pair conversion was happening. So there we saw. So here we realize there is an oscillation, and the moment you put this this neutron-neutron interaction, all of them behave with the same frequency. But then we are saying that this is actually also clubbing the behavior of the nu and nu bar. So nu, so it's not only that all the electron neutrinos of same energy are changing their flavor. The neutrinos and the antineutrinos together are actually changing their flavor to nu mu and nu mu bar. This you can understand if you think of those evolution equations, because those equations I have written, I did not mention it at that time, written for the neutrinos. But all this V dash, because we are looking at some neutron-neutrino scattering, so neutrino and antineutrino can also scatter, right? It's a 4 Fermi interaction, and that scattering, neutrinos and antineutrinos, both of them will come up. So your integral, that interaction term integral, also covers the antineutrinos. So the neutrino, and so it's a coupled system, and this couple is not only between the neutrinos of same flavor, but among them. So this is what people realized, even with this very simplified, what you call is to call the signal angle scenario. And then people just say, okay, now the neutron-neutron, so in the previous picture, you had taken a constant neutron-neutron interaction term, but as I already mentioned that in a supernova-like scenario, this neutron-neutron interaction of the mu would actually fall as 1 by r to the power 4, right? And as you take a supernova toy model, and as you take this neutron-neutron interaction strength to fall down, you actually go like this pendular conversion. You basically see that here is the relative fluxes. So this is where their motion was synchronized. Then you have the pendular conversion, but then you actually eventually have a flavor change. So since the neutrino density decreased, people saw like a complete flavor conversion. And to their surprise, that this conversion happened only in inverted hierarchy, not in normal hierarchy. So I'm talking about 2006, 2007. This is what people realized. Yes, and people wrote many papers on that. I also wrote papers on that. But then we realized that, and there was like, this is like we're going to see like what happened. But then like people were doing phenomenology, but we understood that what you are looking at is not a supernova system, it's not even a supernova toy model, it's your own system where you are saying like all neutrinos are coming with the same angle. So phenomenology, as Moon said, would have looked something like that. So that your spectra, to begin with, is the initial spectra of nu e and nu x, nu e bar and nu x bar, spectral splits in inverted ordering. What would have happened that all the nu e bar and nu x bar, you can see that the flavor, there is a complete swap of their flavor spectra, this red, and so it is after a few hundred kilometers, around 200 kilometers, this has happened. But the flavor asymmetry of the problem should actually remain. So in the nu e, we found that this is going to happen, but above a certain energy. So this is to call the spectral split scenario. And as you can understand how much phenomenology people actually did with that, there are PRL papers with phenomenology with this simple setup. But then what happens if you now slowly start removing these symmetries? That the symmetry arguments that we made, say like let us go not only at one angle, but also let's take this is other angle. So you did not have a phi, now you have this angle coming up. So you had like R and E. Now I have this scenario. So it was only one angle, so basically what I meant by one angle is not considering theta. It's like fixing theta at 45 degree. We used to do calculations with theta equal to 45 degree. And we used to call that, at the single angle approximation, this many neutrinos will be detected in normal ordering, this many neutrinos in inverted ordering. But now I'm going to have different theta modes. So the rho, the density matrix will be now not only on R and E. So there is like another set of matrices going to come up. You have opened up another index, so your problem becomes much more complex. So people did that, and that is to they call the multi-angle and the bulb model. But to everyone's surprise, this scenario remained same, that the results were very similar to what happened in the single angle. See, I mean physicists are not bad at doing approximation. So people said, okay, multi-angle model gives the same result as single angle, and we used to write that like so it was a very great relief, so that I don't have to run the multi-angle model, I can do phenomenology with the single angle. So we used to do that thing. But then this is the same scenario, but as you have realized, so this was happening in the inverted ordering, this bimodal oscillation that you saw, no oscillation in the normal ordering. This spectral split was happening. But then around 2013, you actually put another angle in here, not only theta and phi. So the axial symmetry was taken, and what people found that there were like oscillations happening in normal ordering as well. So like whatever we are doing in last 5 years before that, let's say from 2007, 8, 7 to 13, were like all gone down the river. And but of course, that's a disappointment or some way, but it is also important to understand why was this happening? Why didn't we see this thing? Why are the symmetry arguments so important? This is the thing, the result, what we found at around that time, that if you actually remove the, if you actually now add the phi, so this symmetry used to call multi-azimuthal angle instability, used to call it, and we found that there were, in normal ordering also, there are collective oscillations happening. So, I mean, but as you can understand, like we did not have the stationarity problem, we took a stationary solution, and what people were solving at that time were not PDEs. So we are actually solving mostly ordinary differential equations, and this is very, very very difficult to understand. Like with different symmetries, it's a nonlinear problem. And if you actually make the symmetry arguments with the maximum symmetries, you are going to miss dominant solutions. So this was the picture around 13, 14. But at the same time, we started realizing that actually before that itself, so people realized that there is something called a multi-angle matter separation. What is the idea? The idea is now this actually gives you a better idea of the bulb model. So this is the neutrinosphere. So this is your test particle with momentum q, test neutrino. And for example, you take like one of these things to understand, this neutrino with momentum p coming and interacting with that. And you have to, in such a scenario, you have to integrate over all the different neutrinos coming with momentum p to just get the evolution or the motion of the q test particle, right? Similarly for p, you have to do the same thing. And for all the different modes of angles that you are going to take, that's you see like why people were trying to avoid the multi-angle thing. So for neutrinos, they have the momentum modes. Then for different angular modes, you have to write another set of equations. So there are like large number of equations that people have to write and solve these very stiff differential equations. But then this idea was much simpler to understand. This is called the multi-angle matter separation. What is that? So this is the neutrinos, while they are interacting, all these calculations that I showed were done where you are not looking at the matter around. That is the electrons which is also around these neutrinos. So all the solutions were like just imagining that the neutrinos are actually traveling in vacuum after they have come out of the neutrinosphere. The only thing they are interacting are the other neutrinos. The rest, there was nothing else. But then people realize that they are going through the matter, right? They are going through this electron, and that's going to give different phases. And as they have different phases coming from different angle, so this is going to give this very simple coherent picture may not remain. So the broad idea people had that if the neutrino density around the neutrinosphere is larger than the electron density, I do not have any problem. I can have a nice coherent picture, collective oscillations can happen. However, if the electron density is really high, then these collective conversions can get suppressed. So this is called the multi-angle matter separation, and this was already realized before. But then around this 2011-12, we realized that this is actually indeed, if you look into the supernova simulations, the electron densities are way too large, or at least as large as the neutrinos very close to the supernova core, which for you right now may not seem very, it's a very similar thing. Like it's a simple thing to understand. Like it is a dense star at the core. Why do you expect that only neutrinos are in large number? Electron matter should also be in large number, right? But of course, people did not look into it carefully, because you can also understand this whole evolution is happening parallel to the evolution of the supernova hydrodynamic simulation. So we are just talking to each other and trying to see how it is changing. So then we saw, if you have this multi-matter angle simulations, this is like when you run those codes, we found that these are actually suppressed. So if you take this lambda, remember lambda I was saying the electron potentials term or like signature. Lambda, if it's lambda non-zero, you actually do not get any change. Both inverted and normal ordering in this 1+3 scenario actually get suppressed. So there is no collective oscillations in the early accretion phase. Your life is very simple. You have to you have to look into the Amol's paper, Amol Dighe Smirnov, and that's the oscillation picture that you have to do. But then, what about the cooling phase? The longest phase, the cooling phase has many problems. We will not go into the detail. The first thing is that in the cooling phase, this electron density is actually smaller. So you cannot suppress the collective oscillations in the cooling phase. And on top of that, you have, and people have seen, we have also shown that depending on the choice of certain initial parameter, there can be multiple split in the spectra in cooling phase. So the cooling phase thing is very difficult and better not to touch. On top of that, you can have shock effect and turbulence there as well. So, but then from the oscillation effects point of view, of course, we have understood that the fluxes are very similar near equipartition. Probably the effects are not too long, but so it's better not to do any phenomenology with that. The cooling phase is mostly used for understanding the nucleosynthesis. That we will see if we can have a very brief discussion tomorrow. So the rest of the discussion is now still again with the accretion phase. So this was the scenario in 2013-14. Things were looking rosy, but then what is the understanding of this different oscillation scenario, that as you remove the symmetries, this what we were calling them like a symmetry breaking scenario. So what we did, like to understand it better, what we did is like we went to linearized system. Rather than taking this nonlinear problem, you linearize the equation. How did you do that? So this was this famous paper of Amol and Raffelt with Orko. And what they did is that like, so this was the idea. Idea is this, that what you are interested, so if you remember this matrix of densities, the diagonal elements that tells you about the flavor content. The off diagonal ones are the ones which are telling you about if there is any flavor oscillation happening or not. So to begin with, your matrix has like certain number of different flavors. Your off diagonal elements are almost zero. They are like zero. What happens in the evolution, you want to see how these off diagonal elements are actually evolving. Now, if there is a collective oscillation happening, if there is a what you call the flavor instability, then these off diagonal elements will grow very quickly. So, but to begin with, they are very small. You start with small. So what you do, you basically write the equation of these off diagonal elements. Like here, I have writing the off diagonal elements times of this Q, and I'm going to see if they are going to, there are two of these R's, there will be only one R here. So, and this is a factor what I'm going to see if this off diagonal element starts with this small value Q, but if it is going to increase or like evolve or like grow up exponentially in R or in time. So this is the kind of scenario I take. I put it back into my evolution equation, and this is the kind of equation you get back from there. So if you look into the equation carefully, that's the only equation you have to look. If you look at the equation carefully, that you are actually solving for this Q, and as you can see here for the Q, I have a linear equation because I have got rid of all the nonlinear terms. This is the evolution of Q, and again in the integral, which is coming from the neutron-neutron interaction term, I do not have two different Qs. I have the Q, and this G is basically is one important thing. It's called the spectral difference, or the difference of the flavors that you are looking at, their spectra. We will come to that later. But the important thing is what you are trying to do in the linearized system, you linearize them in the off diagonal elements and try to see if the off diagonal elements are growing or not, right? So this is something we are trying to do, and this basically, and when you look into the growth rate of the off diagonal elements, this is, for example, this is from a nonlinear result, and this is from a linear result. As you can see, when this off diagonal in the nonlinear whole, when you run the whole code, you see there's a flavor probability change, and here you can see the growth rate exactly at the same time actually change. Growth rate means basically this omega, which you can also get from this equation, given a value of mu and lambda. Mu is the neutrino density, lambda is the electron density. If you put them back in, you should get back how the omega is changing, and here you can see how the omega growth. And this clearly showed that this linearized picture gave a very nice way of understanding what was happening. And this is another way of understanding it again in the lambda and this is called the lambda mu plane. And these are the zones, different values of lambda and mu, which is your input, where this instability, flavor instability can happen. And this line, as you can see here, the shock front. So this black line is basically the neutrino, the electron density. If this thing goes inside this instability zone, then you can have a flavor instability. If it remains outside, for example, if it was something like this, you wouldn't have, so you do not actually, so basically what you find in the linearized system, where is this flavor instability and why didn't I see that? So initially when we are doing this very simple system, single angle, we are only finding this solution, this blue one. If I remember correctly, the blue one is for the inverted hierarchy, the red one is for the normal ordering. Now, once we actually added the other angle, this instability also popped up. So this was the difference, and this was the reason why people had this trouble, why we could not find these oscillations to begin with. And then we also did something very interesting. We wanted to see, this is something like, we also put this other two approximations, we got rid of it, like if I'm not only looking at the z direction, but also trying to see what is happening if the evolution in the orthogonal plane, in the x and y direction. So basically, this is still a stationary problem, but we would like to see what would have happened if you had actually also looked into the evolution in the other direction. And we did it with this in the Fourier space. I will not go into the details. And this is the picture. So this is the k equal to 0 is when you are looking only at the radial solution. The moment you try to look for the solutions in the orthogonal plane, you get instabilities, but these instabilities comes at a very far away from the supernova density profile. So eventually, the larger scale modes, that means, see, when I'm saying that I need to look into the evolution into the orthogonal planes, means like I'm just taking that the system is not homogeneous. So I'm not only looking at as a homogeneous system, it's probably enough to look into the radial evolution. But if I have differences coming into the orthogonal plane, but now the question is, how big is this inhomogeneity? What we found, that the larger scale modes are the most dangerous one. The small scale modes are going far away from that. So probably it's a reasonable approximation. It's not bad while doing the radial evolution, but with all angles for the emission. So this was the scenario till 2016. And we were like happy that we have killed collective oscillations, because it's the accretion phase what we are interested, it's already suppressed. But then we somehow stumbled into something called this fast instability. And I think the time is over. Is it okay if I take 10 minutes? Okay, probably people are not okay. But it's good to if you can finish the discussion. If it's more than 10 minutes, we can start from here tomorrow morning. So what about this fast instability? Why did it come? So the physics is pretty straightforward. It's simple. What was happening, you remember, the neutrinos were, this is the last scattering surface. Now, depending on the flavor of the neutrino, you will have different kind of interactions, right, in the supernova environment. So the electron neutrinos, they have all this charge current, they will remain in a thermal equilibrium much longer than the nu mu and nu taus. So nu mu, nu tau, they have actually left earlier from the star, like this green one. The nu e and nu e bar are living much later. As you can see, this is where there's a last scattering surface for nu x, nu e bar and nu e. So now what is your problem? Your problem is you want to look at a certain distance from that last scattering surface. You want to see what kind of interactions they are happening. Now, as you have already understood how important is the angular information. But then this whole analysis till before 2016, we were taking that the angular information for these different flavors are exactly same. But what happens if I now put this tiny difference, which is probably in their angular information? And that actually started this fast oscillation. So this is, and this is the picture that you want to do, 1 plus 3 plus 3. And people started talking about like if I am really looking into that, then probably it's not good enough thing to actually look into a stationary problem. So people are saying, okay, now we have a better numerical understanding. What should we do? Should we look into the non-stationary problem? So this is again this linearized stability analysis, what I have already explained earlier. But I said like this term G, there was this term G sitting over there. It's from a different place, but it's the same thing. There I think we had a G omega and U. Here I have a G, E and V. So what is this G? So G is basically the difference between these flavors, right? The flux difference between these flavors like nu e, nu mu, nu v bar. Now this G depends on both E, that's the energy, and V, that's the angle. So till now, what people were doing as a slow collective oscillation, they were only looking into the energy difference. This spectra, what we call spectra, was only looking to the GE, what people are looking at. Now, if this angular information is important, people need to also look into the V. So this is one scenario where this possibility of fast oscillation was not understood from solving the numerical equations, but rather which was revealed while solving the linearized stability analysis. When he did the linearized analysis and put this angular information into the spectra, so like this, here you can see for the different flavors having different angular distribution. So here is the angle of their emission. As you can, nu V, nu V bar and nu X have different spectra, and if you take the difference, that the difference is what you call the G, you have something called like here you have something called a zero crossing. The zero crossing means that the fluxes actually cross each other, right? So the fluxes will cross the zero. And what has been seen is that this zero crossing is what instigates this flavor instability. So this is called the effect, this electron lepton number on the difference of the nu V and the nu V bar. And once people looked into it, they found that there are instabilities which were coming from the angular spectra. Here is the probability, as you can see. If you take this different this kind of a angular spectra, you will find that the flavor is actually going to change. So now you will probably appreciate more. So this is called the fast oscillation, and they are happening at this very small length scale, and they were coming from the zero crossing in the angular spectra, and the slow oscillation that we spent some time with understanding were actually coming from the crossing in the energy spectra, and this was triggering this kind of flavor instabilities. I mean, about these fast collective oscillations, we have so there are like this is a very active area of research. People are trying to do many things, but let me just give you a very small summary of what we know right now, which probably is good enough for you at this moment. So we have some understanding of these fast collective oscillations. Where, I mean, the question is like some understanding of how this is happening, but where are they happening? Do I have a scenario where I really have? Now the question is, of course, this can trigger, right? So this can trigger, but the question is, do the supernovae have such a zero crossing in their angular spectra? So the result has to again come from the hydrodynamic simulations, but again the hydrodynamic simulations, they are bogged down with so much different inputs and outputs. They actually do not have in the simulation a good angular resolution of their fluxes. So they can happen something called a LISA simulation, where they actually show that the neutrino emission from the star is actually asymmetric in different hemispheres. So in one hemisphere you have more electron neutrino, another hemisphere you have more electron neutrino. These are called the LISA simulations, but these are still in 2D. Probably in 3D one can try to understand it. The implication of supernova dynamics are still not well understood. This is happening very close to the neutrinosphere, but is it going to help the supernova mechanism? The angular information right now is constructed from angular moments, not from the angular information. They are what they give us, the angular moment, and people try to reconstruct them up to some order, but the information is still missing. So from the hydrodynamic simulation right now, we actually do not even have the angular information. And what is the possibility? Possibility of lost neutrino conversion in a pre-shock region of a core collapse supernova. This was done by the group of Nagakura. What they have done, so this is happening in a different way. This angular instability, it's not coming from the neutrinosphere. It's what they're saying, when the neutrinos are going out, they will interact with the other ambient particles, electrons, nucleus, and a part of them will actually come in the backward direction. So not all of them can actually leave the star, some of them will come back. And when they come back, that rate would be different for different flavors. So that is going to give a difference in their angular spectra, and this can happen further out, like around this radius. So basically, where is this thing happening? Is it happening at the neutrinosphere? Is it happening further out? So there is also this mechanism, which is not how the neutrinos are only emitting, but while emitting, how they are interacting with the environment. That also becomes important. Inside the neutrinosphere, in a 3D laser simulation, possibility of first flavor conversion in the pre-shock region of core collapse supernova. But however, as you can understand, all these discussions I did was actually for an effective two flavor model. I did not, all this discussion people were doing from 2016 was only for two flavor scenarios. Then you actually went to look into this problem in a three flavor scenario. Supriyo was doing his master's thesis at that time in Guwahati, and he actually did some of the initial calculations. So this is something we did for a three flavor scenario, and as you can see, this ELN or this spectral difference does not have only two flavors but all flavors. And indeed, around the same time, people started understanding. Now the question is whether the supernovae actually have the difference in their angular spectra for three flavors. So this is the same time around people saw about this mu tau neutrino simulations came out. What is the idea? Sorry, not mu tau simulation. Mu tau neutrino is called the muon simulation. The idea was people are seeing that for certain large stars, while the matter is accreting, the temperature can actually go up, and you can actually have an environment where you can actually create muons. Now from muons and anti-muons, the difference in their flavors is you can see here, their fluxes are actually different between mu and nu mu. So now in this effective lepton number ones where you have both muon and muon, mu and mu bar coming, so your picture with a two flavor where you have only E and E bar is going to change if you look into this kind of hydrodynamic simulations. And we did that, and we found that the results were really different. Here you can see, this is again how you remember the off-diagonal elements tells you about the change in the oscillation. Here we are only looking at the off-diagonal element. The off-diagonal element for a two flavor scenario gives you growth, that is, there can be flavor instabilities. But if you go to a three flavor scenario, you do not have any growth. So the three flavor effects were really important, and this is something we realized. And this is like another case where you can see this is the opposite case where you see like there is no flavor conversion in the two flavor. Here you have flavor conversion in only one kind, but now once you have the three flavors, you have like three different kind of flavor instabilities coming up. So the picture can be like really different in this scenario, and this is like a simulation for what we actually did with a 1 plus 1D. So these are like the results from solving the numerical equation, but only in time, as you can see. But as I have already explained, this problem is actually at least 1 plus 1D. So here is the 1 plus 1D results. This is the instability zone in space and time, how it's going in time. Time is in nanosecond, it's in space. So this is what people have looked into. But then again, the question is like, do you actually have these kind of three flavor crossings there? Because before we were talking about two flavor crossings, there is the three flavor crossings there. So this is from the Garking group results, where again like this is your shock wave. This is a failed model. As you can see, the shock wave radius actually went down, and here they actually pointed out the different crossing scenarios that can happen in their flux. Of course, this is reproduced or like reconstructed from the angular moments, not from the angular information, but that reconstruction showed that in different flavors you can have these angular crossings. So probably these fast oscillations are important, but in this case you can see this is happening after the shock. So we do not know whether this can actually help the shock to revitalize. So all these crossings, so if there is any flavor conversion that would happen after the crossing, it's a failed model, but at least in this case it doesn't seem that these fast oscillations can actually help the failed star. So that's all for today, and tomorrow we will have a better look into the detection prospect of supernova neutrinos. Thank you.
Questions?
So in the first oscillation case, whatever the results is coming, is it the same for normal rotating and inverted rotating also? Or it has the difference between these two?
So you mean the slow oscillations?
In the first oscillation case?
The fast oscillation?
Yeah.
Okay, in the first collective oscillations?
Yeah,
okay.
Fast.
Collective
oscillation.
They're very interesting, very good question. So see, the whole idea was that this fast oscillation, I did not go into that detail, but if you remember that the first oscillation can happen for a vanishing neutrino mass. So this only depends on the neutrino density. It is not sensitive to the mass ordering. However, but does it mean that neutrino mass is not important? Neutrino mass is important. So neutrino mass is important in a sense that in this off-diagonal elements, the neutrino mass actually acts like a seed. So the small angles inside there, this vacuum term, they act as a small seed. So your off-diagonal elements, for example, if you are trying to solve such a system, if you take exact 0 for your off-diagonal elements, you will never get any growth. Of course, if you are trying to solve it numerically, you call it 0, but your machine, your program takes something for 0. It's like a numerical instability which can come up. But if you don't have to even do that, it will basically delay the whole growth. But this is something which is not dependent on the mass ordering, number one. And number two is like, and if such an oscillation is happening, people are trying to look into it like solving these PD equations in many different ways people are trying. So one possibility is like you have a flavor equilibration that I told you yesterday. So it's like a probability becomes 1/3, 1/3, 1/3. If such a scenario, if something like that happens, then probably you don't get much flavor information from the next galactic supernova. But we have to still see what's happening. People are still trying to understand this fast oscillation by solving the numerical.
Another question, like as a whole picture, whatever you showed here, there was no delta Cp till now.
Oh yes. There is no delta Cp. So, I mean, you can see like we have too many things to handle right now. I mean, yes. Okay. Yeah, so if you want to take delta Cp, yes.
So like in supernova, I mean, from the supernova neutrinos, can't we get any information from the delta Cp?
I think people have looked into it. There are papers on that, but for that again, you have to do some kind of a assumption about this this collective oscillation. So you take because as you saw, like these effects are not dependent on the delta Cp. So the effect can come only from the vacuum and the MSW part, right? And if you do that, but then like if you do not understand the oscillation from the neutron-neutrino interaction part, your phenomenology is again like what we are doing in 2006-07.
So in that case also in 2000 paper also you can see that there is that P and P bar is there, and the P and P bar is totally independent of the delta Cp. Like if I take only the MSW case, no collective effect case. So if I take that one into the picture in the 3 flavor oscillation, then maybe delta Cp will come, or even also there will be no delta Cp will come.
No, what I'm saying is like you can do this whole analysis with delta Cp, but the point is like, but eventually you want to do some phenomenology, right? And the phenomenology, you don't have a better understanding because you still don't understand the oscillation part from the collective points of view. So whatever is your information, you can make an assumption, okay, let me say that the collective oscillation is suppressed. Then you can do the analysis. Or you say, okay, I take a certain result for the collective oscillation, and on top of that, let me see what is the delta Cp phenomenology I can do. In that regard, I am saying that like, that would be till like, I mean, till you don't have the whole understanding, it's not like, it's probably, okay, not very clear like phenomenologically.
Okay, so let us thank Sovan again.